Okay, here are the answers to the quiz on electromagnetic induction and alternating currents. 100 kilowatts is transmitted down a 6 ohm line at 1000 volt. How much less power would be lost if the power were transmitted at 3000 volt instead of at 1000 volt? So you have the power given, you have the voltage, so we can find the current. Power is the product of current and voltage, from which we can calculate the current. It's 100 amperes. And therefore the power lost is generally in the form of heat, which is I squared times the resistance. So 6 times 10 to the power 4 watts is lost. If it was transmitted at 3000 volt, then the current would have been 3 times less, 100 by 3 ampere. And in this case, the power lost would be, again, using the same formula, the square of the current multiplied by the resistance. Obviously it is less, and therefore the difference gives the answer, because the question says how much less power would be lost. .33 times 10 to the power 4, which is 53.3 kilowatts. 2 amperes in the 100-turn primary of a transformer causes 14 amperes to flow in the secondary. How many turns are in the secondary? So you have IP and you have IS, and we know that the power in the primary is equal to the power in the secondary. And you can rearrange that to give this formula, but we also know that the ratio of the voltages is, oh, that's a mistake. I need to have this as number of turns in the primary. I'm going to change that. Okay, so comparing these two equations, you get this. And now substitute what's given to get the answer as 14.28 ampere. A uniform magnetic field is applied perpendicular to the plane of a 60-turn circular coil with a radius of 6 centimeter and a resistance of 0.60 ohms. The magnetic field increases from 0.2 Tesla to 1.8 Tesla in 0.20 seconds. What's the EMF induced in the coil? That's the coil, and the magnetic flux is perpendicular to the coil, so maximum flux is passing through it, and by Faraday's law, E is minus d phi by dt. In this case, it's dB by dTA. The reason is phi is actually B times A. So when you take the derivative, you're going to see that the area is constant, so you have it outside and it's dB by dt. Now the change in magnetic flux density is 0.2 minus 1.8, and the area of the coil is pi r squared, radius is in meters obviously, and you get 5.4 volt. That is the induced EMF. In this question, it's a 20 turn coil, area given, and again the magnetic field is perpendicular to the plane of the coil. No, it's not. It's actually making an angle of 30 degrees. So the perpendicular that's drawn to the coil is making an angle of 30 degrees. And what is the flux? Flux is the dot product of B and A. So phi is B dot A, which is B times A times cos theta. And theta is the angle between the magnetic field and the perpendicular drawn to the coil, which is actually given here. So it's a direct substitution of those numbers that gives you 0.0152 Tesla meter squared. A transformer question again. The number of turns in the primary is given. And the number of turns in the secondary is there. The voltage applied to the primary is given. Find the voltage in the secondary. Simple question, because the ratio of the voltages is equal to the ratio of the number of turns. Absolutely no explanations required there. It's just substitution. And obviously this is a step-up transformer, so since the ratio of the number of turns is 400 and 400, the voltage should be 4 times greater. So 120 times 4, 480 volt. And this question says it's a constant magnetic field. It's a constant magnetic field. And what is, if the area of this loop is changing, what is the EMF induced in the loop? Okay. Once again, you apply Faraday's law. E is minus d phi by dt. And remember that phi is equal to B dot A. But in this case, B is constant. So you're going to get B dA by dt. Okay, B dA by dt. Now, the change in the area is given, isn't it? The change in the area is given because you have the final and the initial values. The difference gives you the change in the area, and 0.7 times, and I forgot to divide by the time, so 1.6 seconds. When you divide that, you get 4.375 times 10 to the negative 4 volt. Is the answer. Number 7, a generator produces 60 amperes of current at 120 volt. The voltage is usually stepped up to 4500 volt by a transformer and transmitted through a power line of total resistance 1 ohm. Find the number of turns in the secondary if the primary has 200 turns. So you have IP 60 ampere, VP is 120 volt, the secondary voltage is 4500 volt. You have to find the number of turns in the secondary. Number of turns in the primary is 200. Now Vs by Vp is equal to Ns by Np again. And when you calculate that, you get 7500 turns in the secondary, while the primary only has 200 turns. Obviously, this is again a step-up transformer. 8. At what rate would the current in a 100 millihenry inductor have to change to induce an EMF of 1000 volt? The EMF induced in an inductor is given by minus L times di by dt. We require an induced EMF of 1000. The inductance is 0.1 Henry because it's 100 millihenry, and you're asked to find the rate of change of current, which is di by dt. So that is just 1000 by 0.1. And of course the negative sign has been neglected because it only shows the direction. So the answer is 10,000 amperes per second. What is the inductive reactance of a 20 millihenry inductor at a frequency of 60 Hz? Inductive reactance is 2 pi times the frequency times the inductance. Straightforward, everything given, just substitute. It's 20 millihenry, so it's 20 times 10 to the negative 3. 7.5 ohm. If the AC peak current through a 100 ohm resistor is 17, that's 1.7 ampere, sorry. What is the average power dissipated by the resistance? Okay, so the peak current is given. We can find the RMS current using this relation. Peak divided by square root 2. That gives 1.20 ampere. And the average power is just the product of I squared RMS and the resistance. (144 watts). A 25 millihenry inductor is connected in series to a 20 ohm resistor through a 15 volt DC power supply. The switch is closed at t is equal to 0 seconds. What is the time constant? A big story, you don't need all that. Just know that the time constant is the ratio of the inductance to the resistance. Both values are given. 25 millihenry divided by 20 ohms, it gives 1.25 times 10 to the negative 3 seconds. An inductor has a current given by that equation right there, and the maximum EMF across the inductor is equal to 0.5 volt. What is the self-inductance? Okay, voltage is the product of current and inductive reactance. That's just Ohm's law. But omega is 275 radians per second. How do you know? Because when you look at this equation, actually the equation should be I is equal to I naught. So the maximum current is 0.5 ampere cos omega t. So in place of omega you have 275. And not only that, the maximum current is 0.5. So since you have the maximum voltage and the maximum current, and XL is omega times inductance, right? Rearrange that. You get 1 by omega, which is 1 by 275. That is 3.64 times 10 to the negative 3 Henry. A coil with a self-inductance of 6 Henry has a constant current of 2 ampere. Oh, it's a constant current. Point to be noted. It's a constant current. The current is not changing. If the current is not changing, the magnetic field is not changing. And if the magnetic field is not changing, there is no induced EMF in the coil. Di by dt is 0. Therefore, induced EMF is nothing. A solenoid of length 5 centimeter has a cross-sectional area given and 300 turns, and over this solenoid you have a secondary winding of 180 turns. Okay, so what's the mutual inductance? Mutual inductance, now that's the length given, it has to be in meters, and the area is in centimeters squared, that has to be in meters squared. Okay, and mutual inductance is given by mu naught N1 times N2 times the area of cross section by the length. Okay, mu naught is 4 pi times 10 to the negative 7, multiply with the number of turns there, area of cross section and the length. Get the answer is 1.4 times 10 to the negative 4 Henry, which is 0.14 times 10 to the negative 3, so 0.14 millihenry. Okay. When a 60 hertz voltage is applied to a 22 microfarad capacitor, what's the capacitive reactance? The formula XC is 1 by 2 pi FC. Everything given, substitute. Just need to let this run by, okay? And micro is 10 to the negative 6, so you get the answer. 121 ohm. And here it says the phase angle of an LRC series circuit, inductive reactance given 200 ohm, capacitive reactance 100 ohm, and the phase angle is 40 degrees. Phase angle is given by tan phi equal to XL minus XC divided by the resistance. And therefore the resistance is XL minus XC divided by tan phi. (200 minus 100 divided by tan of 40 degrees). That gives 119 ohms. Brings us to the last one. What would be the resonant frequency of an LRC circuit with resistance, inductance and capacitance given? Resonant frequency does not depend on the value of the resistance. It's given by the formula 1 by 2 pi square root L times C. And that is in millihenry, so 25 times 10 to the negative 3. Capacitance is microfarad, 30 times 10 to the negative 6, and you get 183 hertz as the frequency. Thank you and good luck.